So I wanted to take a look at a few more examples of functions and identifying what types of discontinuities it ends up having. So that kind of comes in two stages. First, we got to figure out where it has discontinuities, and then second, we got to figure out, whether those are removable or not. So remember, removable discontinuities, you can think of them as a hole in the graph, whereas a non-removable discontinuity is more like a break in the graph, like the limit just straight up doesn't exist, or So so we got this guy right here. So it's a slightly more involved rational function, than some of the ones we dealt with. We've got a third degree polynomial up top and a quadratic down below. X cubed minus x squared minus 2x divided by the quantity x squared minus 5x plus 6. Now, as I've said, tracking down where discontinuities occur is pretty much identical to determining the domain of the function, figuring out where, like some sort of, mathematical no-no would happen if we tried to plug in an x coordinate. Here, division by 0 is really like the only bad thing that could happen, right? So we need to figure out where this thing is 0. Shock and dismay. We need to factor stuff. So the denominator factors, as beat. So x minus 2 times x minus 3. So again, feel free to verify that if you didn't, pause and then work that out while I awkwardly said the word beat. Anyway, so from looking at this, as far as continuity is concerned, the numerator doesn't particularly matter at this stage. Either, as you're saying, any x value that makes this thing be 0 is automatically a point of discontinuity. We would have to go, personally fill in a gap, even if it is removable. So I guess I should say has discontinuities at x equals 2 and x equals 3, because 2 would make this piece 0, 3 would make the second piece 0. Now it comes to classifying these monsters. Now, that's where dealing with the numerator is going to be kind of important, right? So now if we factor the numerator, you might recall if we were trying to work out a limit, we can, in the sense of a limit, cancel terms that are causing problems. So it means we need to factor this thing. Good news, everything has a common factor of x, so we can just kind of pull that guy off right away. That would leave you with x squared minus x minus 2. And you should be able to confirm that that's how that guy breaks down. That's one of the ugliest plus symbols I've written, in the last 5 minutes. So, still not great, but there we go. At least it looks moderately like a plus now. So x times x plus 1 times x minus 2 over x minus 2 times x minus 3. Now again, in terms of this being a function, we can't just cancel those off. But if we were evaluating a limit of this thing with a limit right here, then yeah, what we said before in section 1.3 means we could cross those out. So those would be gone, and then we don't really have any problems anymore at x equals 2. So that guy, as it turns out, is a removable discontinuity. On the other hand, if we look at x equals 3, well, there's nothing to get rid of that x minus 3 term, right? So as it turns out, that is what we would call a non-removable discontinuity. So there would, in fact, be like a full-on break in the function at x equals 3, whereas at x equals 2, we would just have kind of like a little, hole that, we draw, and then we could plug in with the appropriate limiting value. All right, so that's one example. Let's take a look at another one. All right, new example. So in the numerator of this guy that I cleverly renamed g of x, just to keep you on your toes, we have x squared minus 25 in the numerator. Down below in the denominator, we have x cubed minus 10x squared plus 25x. So you kind of have the idea at this point. So to track down where things are bad, well, again, like we saw in the last example, we can factor an x off this thing. So Maybe I should have been a little more creative and had you pull off like an x squared and bumped all the powers up, but I'm not going to redo it at this stage. Anyway, so now if we factor this thing, after you pull off the x, you have x squared minus 10x plus 25. That would look like this. X minus 5 times x minus 5. If you had written x minus 5 quantity squared, that's fine by me. So from looking at this, we're going to have points of discontinuity at x equals 0 and x equals 5. So again, remember, 0 makes x 0. 5 makes both of those 0, so it's not like it's double bad or anything. So, all right. So now it comes to classifying these things. Well, now we got to factor the numerator. So that's a difference of squares. So we'd have x plus 5 times x minus 5 up in the numerator. And at this point, you look, well, we don't have any term up here dealing with this x that's hovering around by itself. So that one is a non-removable discontinuity. Nothing removes the badness, so to speak. Then we come in at x equals 5, and you may look at this and you say, oh, well, yeah, we could, again, if we were working out a limit, we can cross both of those guys out. Does that make it removable? You might think so, but there's kind of a problem. Yeah, even if you cover those guys up, if you plug in x equals 5, you're right, bad things happen. You still got a term that causes a zero denominator to occur. So in this instance, both of these are non-removable discontinuities. So this particular function, its graph wouldn't have any holes in it at all. It's got nothing but a pair of kind of clean breaks, so to speak. All right, so we've done a little bit of classification. I want to shift gears a bit and talk about one other type of function that we haven't quite addressed just yet. Admit it, you were expecting a trig function to be right here. That's okay. The trig functions are perfectly valid to talk about in and of themselves, but the sine and cosine functions are continuous for all x, so, and then the other trig functions are all defined using them, so it's, it's not that it's not worthwhile to talk about, it's just that there really isn't that much there. All right, so this guy is a piecewise defined function, so that's, kind of, something we've, talked about from time to time. What formula we use depends on whether or not the x value we're interested in is here, less than or equal to 3, or greater than 3 on the other hand, left versus right, so to speak. So, as it turns out in this instance, any point other than at 3, like anywhere other than 3, you're just using either this linear guy, which is a polynomial, and he's perfectly fine, or a quadratic, which is also perfectly fine on its own. So the only point we need to be worried about in terms of continuity is x equals 3. And our tool for dealing with that is going to be to consider left and right hand limits in this instance. So I've got my left hand limit of p of x as I approach 3 again. These numbers are all going to be less than 3 for this purpose. That's what the minus tells me. So that means I'm focusing on this guy because all of my x values are less than 3. So, and at this stage, like we saw in our, some of our previous examples, from here, I can just do a direct substitution. Now that I'm no longer worrying about both sides of 3 at once, I can just do a direct sub, and plugging x equals 3 into this thing gives me 3 plus 1. That's 4. All right. Let's see what's happening from the other side. Okay. So, right-hand limit with the plus, that means my x values are all greater than 3. So now I'm using this guy. So the limit as x approaches 3 from that side of just x squared minus 1. If you do that direct substitution here, 3 squared is 9. 9 minus 1 gives me 8. Last I checked, 4 is not equal to 8. So So I'm short on board space. So I have a non-removable discontinuity because this tells me that the limit doesn't exist, and that's what it means to be a non-removable discontinuity. So for this particular problem, we've got ourselves a discontinuity at x equals 3, and it turns out to be non-removable. Now, however, it does end up being the case here that the function value at 3, according to this, we would use this branch at x equals 3. So we would plug 3 into this thing. So note that the left-hand limit matches our function value. So the left-hand limit does in fact match p of 3. So it turns out, just like we had one-sided limits, we can have one-sided continuity. So it's left continuous at x equals 3. On the other hand, if instead of having the equal to here, I had the equal to on this other branch, the x squared minus 1, then the right limit would match up with our function value, and we would say instead of being left continuous, this thing is right continuous. All right, so I want to check one more thing. I'm going to tweak this very carefully, and then we're going to revisit real quick, all right? All right, hopefully this isn't like a blink and you miss it thing. It's pretty clear. I've taken my piecewise function and I've adjusted things, but I've slapped a coefficient of 1/3 on both pieces of this thing. So the process still ends up working out the same. Anywhere other than 3, we're hunky-dory. Now let's check our left and right hand limits at that possible junction point at x equals 3. From the left, we use the linear guy. So 1/3 times 3 plus 1 if we do our direct substitution. 1/3 of 3 is 1. 1 plus 1 is 2. Sorry. Yeah, 1 plus 1 is 2. I freaked myself out there. All right. The right hand limit. Now, I'm only dealing with the quadratic branch. I can still direct sub, though. So I would have 1/3 times 3 squared. So 1/3 times 9 is just 3. And 3 minus 1 is, in fact, 2 in this case. So this particular function, by adjusting these guys, by putting the right coefficient up there, it turns out we're able to sort of make the break, line up, so to speak. So this doesn't have any discontinuities, or it's continuous for all x, or continuous on negative infinity to infinity, however you want to phrase that. All right. I just wanted to hit this example, kind of really quickly in a context where you got to see that just because a function is piecewise defined doesn't automatically mean you've got a discontinuity at the breakpoint. You do need to dig in and investigate rather than just say, limit automatically doesn't exist because curly brace. All right. So that wraps up what I'm wanting to talk about continuity and discontinuities in this section. But we're actually going to dig in a bit further into that notion of discontinuity when we talk about the stuff in section 1.6. So yeah, foreshadowing. It's a thing.